So we are starting system of linear equations, and already you have the idea that a system of linear equation can be consistent, can be inconsistent. From our last class you know this thing. So if a system is consistent, that means it has solution. If a system is inconsistent, then that has no solution. So whenever we have a consistent system, then there will be two possibilities. It may be with one solution, it may be with many solutions. So you already have the idea of system also. System of linear equation means you have some equations where the variables are with power 1 and you have more than one equation. That's why the equations are linear, and since we have more than one equation, so that's why those equations combinedly are known as system. So system of linear equations. So one example can be, let's say you have 2x plus 3y equals 5. This is a linear equation because here x power 1, y power 1. We may have, let's say, 3x1 plus 4x2 plus 3x3 equals, let's say, 5. So this is another equation. This is also linear. Instead of xy, here I have written x1, x2, x3. I can also write the same equation in this format. Let's say we have 3x plus 4y plus 3z equals 5. So instead of x1 I can write x, instead of x2 I can write y, instead of x3 we can think about z. So one thing is that variable is not important. The important part is what is the power of the variable. X variable has power 1, or x1 variable is with power 1, y variable is with power 1, x2 variable is also with power 1. Let's say z variable is with power 1. Instead of z we can also write x3. So x3 is with power 1. So this is about linear equation. So instead of x, y, z, we can also think about x1, x2, x3. So if we write the variable with some suffix, let's say xi, where I equals, let's say 1, 2, 3, 4, up to infinity that we can consider. So this is the easiest way or convenient way to write any equation with any dimension. So if we write x, y, z, that is not a problem. But just to have the generalized or global concept, we can also use suffix x suffix 1, x suffix 2, x suffix 3. So here x1, x2, x3 all are variables that are acting as x, y, z. So we are actually solving this type of equations. So suppose we have to solve this equation. Here we have only one equation and this equation is linear. So this is known as linear equation. But if we have, let's say, more than one equation of similar pattern, let's say we have 2x plus 3y equals 5 and minus x plus 6y equals 7. Now combinedly we have a system. Since we have more than one equation, this is comprising a system. So we have system of what type of equation? All are linear equation. Have a look on the first equation, we have x power 1, y power 1. Have a look on the second equation, we have x power 1, y power 1. So that means if we have to solve this system, we know many methods to solve this system. In elementary school level, we have learned how to solve this type of equations. And you will get the solution in a pair form. You are actually finding the solution for x and y. That means x, y is forming a pair. And how many solutions you have? You have actually one solution. Together x and y, you are getting one solution. So solution means if you input the value of x and y in the first or in the second equation, the left side and right side will be balanced. So same thing goes for three variable problems. Suppose you have 3x plus 4y plus 3z equals 5. You may have some other equations here also. Let's say minus x plus 2y plus 4z equals minus 7. Suppose you have 2x minus y plus 5z equals 2.5. So now have a look on these three equations. These three equations are actually forming a system. System of what type of equation? System of linear equations, because the first equation has the variables x, y, z and all variables are with power 1. The second equation has the variables x, y, z and the powers are 1. The third equation has the variables x, y, z with power 1. So combinedly we have a system. So system of linear equations. So we are actually going to solve this type of system of linear equations with the help of a new technique, with the help of a new method, and the method is known as Gaussian elimination method. So this method is named after the German mathematician Carl Friedrich Gauss. Okay, so now we know as this is Gaussian elimination method. There is also one modification of this method that is known as Gauss-Jordan method. Another mathematician, Wilhelm Jordan. So based on this method we have a modification that is known as Gauss-Jordan method. So both methods can be applied to solve system of linear equations. But whatever we have learned in our secondary school level, so that are substitution process, that may be elimination process. In college level we have learned Cramer's rule. So that are actually the basic methods that we have learned. But here we are going to actually study or go through Gaussian elimination method. So before going to describe the method, at first we have to understand the short form of a system of linear equation. So suppose we have a system of linear equation. Let's say we have a system of linear equation. Let's think about one example. Suppose we have 2x plus 3y plus 4z equals 5. But instead of x, y, z, I am going to write this time x1, x2, x3. So we have the first equation with the variables x1, x2, x3. So these are the variables that we can see in this linear equation. Suppose we have another equation minus x1 plus 2x2 minus x3 equals 4. So this is another second equation. This is also linear because all the variables x1, x2, x3 are with power 1. Now suppose we have another equation 5x1 plus 3x2 minus 6x3 equals minus 2. So this is the third equation that is also known as linear. Now if we think about all the equations together, this is actually forming a system. Actually a system of linear equations. So this is the system of linear equations. Now if we have to solve this system of linear equations, that means the solution that we are going to have, that will be x1, x2 and x3. We don't know what is the solution, but the solution will come up in this format. You will get the value of x1 you may get the value of x2. Also x3 can be found. Together we have x1, x2, x3. So that is the solution. So this system of linear equation is actually one system in 3 variables. How many variables we have? There are 3 variables. How many equations we have here? 1, 2, 3. We have also 3 equations. So if we have to solve these equations where we have 3 variables and 3 equations by Gaussian elimination method, then at first we have to understand the general concept of a system. So you can see that here 2, 3, 4, minus 1, 2, here minus 1, 5, 3, minus 6, all are the coefficients or constants that are attached with x2, x3, also with x1. So these constants or these coefficients can form actually a matrix. In last session we have learned so many definitions. We have learned what is the definition of a matrix, what is rectangular matrix, square matrix, scalar matrix, diagonal matrix, identity matrix. We have also learned determinant, minor, cofactor. We have also seen the definitions of non-singular matrix, singular matrix. So we have already the idea of matrix. We can transform all these equations to matrix notation. So here have a look. The system that you can see here, there are 3 equations with 3 variables. Now suppose we may have, let's say, 5 variables, x1, x2, x3, x4, x5, and let's say we have 7 equations. So this may be possible. Okay, it doesn't mean that always the number of variable and number of equations will be same. It may be different. That means you have to know the general idea. So suppose we have, let's say, one equation in this form: a11 with variable x1 plus a12 with variable x2 plus a13 with variable x3. Have a look. Let's say this is a11, 2 is a11, and there is x1. a12 is 3, and then we have x2. a13 is 4, and we have x3. So this is how I am writing. So we have this, and this thing is continuing. Suppose a11 x1, a12 x2 plus a13 x3 plus a14 x4 up to a1n xn equals, have a look, there is one equal sign here with some values, let's say 5, 4, minus 2. Let us consider these values as b1, b2, b3. Let's say the first value is b1. Now let's think about the second equation. Similarly, we have a21 x1, a22 x2, a23 x3 up to a2n xn, and there is a value that we can see on the right side, that is, let's say, b2. So whatever I am writing here, that is the theoretical approach in n number of variables. How many variables we are considering here? x1, x2, x3, x4, x5 up to xn. This n can be infinity. That means the number of variables that we have is actually here n. So if we think in this way, then we can solve, or we can have the motivation to solve any system with any variables with any equation. The number of variables and the number of equations will not matter. Okay, so that's why we have to know the general system, so that we can have the entire idea how to solve a system of linear equations. The method is very easy, but you have to know that that method can be used to solve not only equations with 2 variables and equations with 3 variables like this. That Gaussian elimination method can be applied to any system where we have many equations and many variables. So that is the main case why we are learning this one. So similarly, let's say we have a31 x1 plus a32 x2 plus we have a33 x3 plus a3n xn equals b3. If we try to think about, let's say we have many equations, so this thing is continuing, and lastly we have a m1 x1 plus a m2 x2 plus a m3 x3 plus a mn xn equals, let's say here we have bn. So we can also write bm, no problem. So you can see that this time we have number of variables. How many variables we have? x1, x2, x3 up to xn. We have n number of variables. Now think about the equations. How many equations we have? 1, 2, 3 up to m number of equations we have. So this is the global perspective of a system of linear equation. All the equations that I have written here with theoretical notation, all the equations are linear, because have a look, x1, x2, x3, x1, x2, x3, x1, x2, x3, even xn, 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 all are with power 1. So that means all the equations are linear. Since we have more than one equation, so this is actually forming a system. Combinedly, we call this one a system of linear equations. Now, from this system of linear equation, if we want, we can transform these equations to matrix notation, and that will be easier to write. So the easiest short form is this one. So whatever we have here, that can be transformed to matrix form. Suppose we have AX equals B. So this is actually the short form of the previous system. So whatever we have here, that is written in short form. This whole thing is representing the previous equations with m number of equations, n number of variables. So this is a powerful equation that you can see. So here A, X and B all are matrix. A is a matrix with some size or order. X is a matrix with some size and order. B is a matrix. Okay, so now if I write what is A, what is B and what is X, then you will get the idea. So we can write this system into the short form. This is the short version. Now we have to know what is A. So here A is a matrix. A is a matrix that will come from the coefficients of the equations. So you can see that this is the system that we have here. So the variables are x1, x2, x3, xn. So with this variable there are some constants that we can see. Think about this example with variables x1, x2, x3. The constants are 2, 3, 4. So if we think about these constants or the coefficients, then we can think about a matrix. That matrix is A. So here, from the previous main system, we can think about all the coefficients A11, A12, A13 up to A1n. So from the first equation, we have just taken the coefficients of every variables x1, x2, x3, xn, and these are A11, A12, A13, A1n. Similarly, from the second equation, we can find A21, A22, A23 up to A2n. Similarly, A31, A32, A33 up to A3n. And if we go in this way, you can see that we have the last equation here, that is AM1, AM2, AM3 up to AMN. So this is our last equation, and so we have taken the coefficients of every variables from the last equation, and now you can see we have a matrix. This matrix has m number of rows, n number of columns. So the size or order of this matrix is m by n. Okay, this is the size or order of the matrix. So now we can understand that the short form that we can see here, we have A, x equals b. So already you know what is A. A is this one. That means A is known as the coefficient matrix. So A is known as the coefficient matrix because we have collected all the coefficients and we have written in this way. Now we will talk about X and B matrix. So here A matrix is the coefficient matrix. Besides all the definition from our last class, you have to also know what is a coefficient matrix. So a coefficient matrix is a matrix that is coming from a system of linear equation. If we consider all the coefficients, then we will get this. Now, what is X? X is all the variables that we have. Okay, you can see that in this equation we have x1, x2, x3 up to xn variables. So this is the case. X is a column matrix where we have x1 variable, x2 variable, x3 variable up to xn. So we have already mentioned that we have n number of variables here, and that's why we have x1, x2, x3, xn. So here you can easily understand that this X is actually denoting the solution set or solution matrix. Okay, A is denoting the coefficient matrix. X is the solution matrix. Solution means if we think about this system where we have three equations with three variables, so the solutions x1, x2, x3, if we write x1, x2, x3 in short form capital X, then that is actually meaning the same. Okay, so all variables in compact form can be written with capital letter X. Now what about B? B is actually the right side values that you can see, B1, B2, B3 up to Bn or Bm. Have a look here, the example that you can see. If we think about 5, 4, minus 2, then that is the B matrix. So from the general equation, we can now think about what is matrix B. So matrix B is also a column matrix. We have B1, B2, B3 up to, let's say, Bm. So what is a column matrix? A column matrix is a matrix where we have many rows but only one column. Have a look. You can see here we have 1 row, 2 row, 3 row, n number of row. So first, second, third up to nth row. That means we have n by how many column we have? Only one column. So the size of this matrix is n by 1. Similarly, here how many row we have? We have m number of rows. How many column we have? We have one column. So if we have only one column, then that is known as column matrix. Similarly, same thing goes for row matrix. If we have only one row and many columns, then that is known as row matrix. So here we just need column matrix definition. So this B is actually the right side values that you can see in the main system. So now this Ax equals B is actually the short version of the main system. So here Ax equals B, this is actually known as a system that is non-homogeneous. So this is the definition of non-homogeneous system. So what is a homogeneous system? If Ax equals 0, suppose the right sides are 0, then that is known as homogeneous system. If we think about one example, then it will be clear to you. Suppose you have 2x plus 3y equals, let's say, 0. You have 4x minus 3 by 2y equals, let's say, 0. So this is a system where we have two equations with two variables. The right side values are 0. All values b1, b2 are 0. That means this system is obviously a system of linear equations in two variables x and y with two equations, first equation, second equation. But is it homogeneous or non-homogeneous? So since the right side values are 0, so this is homogeneous system. So if we try to write this system in compact form, then we can write by this way. That is 2, 3, 4 minus 3 by 2 times how many variables we have? X and y equals 0, 0. So that means whatever we have here, the system is converted to matrix form. And that is the important part, because we are going to learn a new technique, that is Gaussian elimination technique. So in Gaussian elimination technique, always you have to convert any system to matrix form. Have a look. If we think about this problem that is already solved here, so you can see that the system that we have here, that is with three equations and with three variables, but we have converted the system in a matrix form. So that is the important case that I want to share here. So you can see this system has been converted to a matrix A, a solution set X, and the right side values that are only constants, there is no variables here, that is B. So this is our A matrix, coefficient matrix. This is our X matrix known as solution matrix or solution set. This is our B matrix, based on which we can say whether the system is homogeneous or non-homogeneous. So that means if B is not 0, then that is non-homogeneous system. If B is 0, then that is known as homogeneous system. That is the simple thing. So this is the idea of homogeneous and non-homogeneous system, and how to convert any system of equations to matrix form. So suppose we have another system here, 2x plus 3y plus 4z equals 5. Let's say we have minus x plus 2y plus 3z equals 7. Let's say we have here 4x minus y plus 2z equals minus 8. So we have a system. If we have to solve this system by Gaussian elimination method, first of all we have to convert it to matrix form. So if we think about just the coefficients, then we can consider one matrix, that is 2, 3, 4, minus 1, 2, 3, 4, minus 1, 2. This matrix is known as the coefficient matrix. We have just collected the coefficients from this system of equations and we have written in a matrix form, that is matrix A. How many variables you have? You can see x, y, z. So we can think about the main solution set X equals x, y, z. This is the column matrix. Think about the right side values. We have here B, that is 5, 7, minus 8. Now the system that you can see here can be written in short form, AX equals B. This is a non-homogeneous system because the right side constants are actually non-zero. Here we have values. If all the constants of the right sides are 0, then that is known as homogeneous. So this is a non-homogeneous system. So if we try to think about this AX equals B, where A is this matrix, X is this matrix, B is this matrix, then you will actually get the short form of the system. So this is the prerequisite, what we have to know first. Now let's get back to the main part. A system may be consistent system, may be inconsistent system. Some system may have solution, may not have solution. If the system doesn't have any solution, that means the solution set X is not found. So in that case, that system is known as inconsistent system. A system is known as consistent if it has solution. Solution can be one solution or unique solution. Solution can be many solutions. So from the last class, you know that I have already mentioned what are the conditions of having one solution, many solution, no solution. So if we think about, let's say, equations like this, here you can see, suppose we have, let's say, 2x plus 3y equals 5. So if we try to convert this to y equals mx plus c, then you can easily do that. So the main thing is the equation that we have in two variables, x and y only, that are actually straight lines. You will get straight lines like this. You have total two equations. You will get line 1, you will get line 2. So what is the condition of having one solution? Suppose you have two lines or two equations. This is line 1 and this is line 2. If the lines are intersecting at a common point, then you have only one solution. Here you will get x comma y. Similarly, suppose you have two lines, line 1 and line 2, but these two lines are parallel. If the slopes of the two lines, let's say slope m1 and slope m2, are same, from the concept of line you know that there is a concept slope. So if the slopes of the lines are same, then that lines are parallel. So if there are parallel lines, so there is no option for intersection point like this. So at that time there will be no solution. Similarly, if we have, let's say, line 1 and we have also line 2 that is just lying on line 1. So line 1 and line 2 are actually same line. That are actually same equations. So the two lines apparently may be looking different, but they are same and the graph are same. So the graphs are same. So it means the lines are coinciding on one another. So at that time there will be many intersecting points. So you will get infinitely many solutions. So this is about equations with two variables, x and y. Suppose we have 3x plus 2y plus 4z equals 7. And similarly we have another second equation, another third equation, and that's why you are having a system. So if we have only x variable and y variable, we know that that will be a line. So that is in two-dimensional plane. If we have both x, y, and besides x, y, we have also z, then that is not confined in 2 dimension. That is in 3 dimension. So to draw the graph of this equation, we have to have x, y, z. So this time you will not have a line, rather you will have a plane. Plane means there is, let's say, a paper. Think about a page. Think about one A4 page. The A4 page is actually a plane. Let me give you one geometrical view. So suppose you are drawing 3x plus 2y minus 4z equals 6. So have a look. This is not a line now. This is a plane. This is a flat sheet. Have a look on the shaded region. This is a flat sheet. So this time solutions can be possible if you have, let's say, 3 equations, and this time this is not in 2 dimensions, this is in 3 dimensions. So there will be 3 equations, there will be 3 planes. If the planes are parallel, that means there is no intersection, so there is no solution. So the system will be inconsistent. Suppose the lines are intersecting, then you know that there will be one solution. So similarly, in 3-dimensional case, you have 3 planes and the 3 planes have intersection. That means there will be solution. There will be one solution. If the planes are lying one another, they are coinciding, the 3 planes are same, at that time there are many intersections, there are many points, so there will be many solutions. So this is how you can think about 2 dimension, 3 dimension. If we increase the number of variables, Suppose we have one equation with x, y, z and w. In that case, you have to think about 4 dimension. So that is out of the scope here. We can't draw the graph even with the tool that we are using here, GeoGebra. Okay, but mathematically we can analyze, because we know that all variables can be considered as a single matrix X. Okay, so solution can be found. So that's why I always say that human eyes can just see or visualize up to 2 dimension and 3 dimension, but the higher dimensional cases, think about a manifold. You don't know what is the definition of manifold, but actually this is higher dimensional concept. So if we think about the higher dimensional equations, at that time Gaussian elimination method will help you to get the solution directly or in a fastest possible time. Okay, so that is the motivation why we are learning this method, Gaussian elimination method. So this is what we have here at first to know. Now let's start what is a Gaussian elimination method. I have already mentioned that in your elementary school level or college level you are familiar with many methods and you have solved this type of equations several times. But those equations were just valid for one solution. But here we are generalizing the concept since we are in advanced level now. So we have to think with global perspective. A system can be with one solution, can be with many solution. This is one exception. Can be with no solution. Whatever we try, we will not get any result. That means the lines, if we think about 2-dimensional case, are parallel. The planes, if we think about 3-dimensional case, are parallel. Suppose we have 4-dimensional cases, all the shapes that we have from one equation, one system, are parallel. There is no intersection, so there is no solution. That is the geometrical aspect. So what is Gaussian elimination method? I have already written here. There are some steps that you have to follow. So you can see that there are 4 steps: step 1, step 2, step 3, step 4. So let me describe all these steps. So first of all, suppose you have a system AX equals B. I am writing in short form, but this short form can be coming from a larger scenario. Have a look here. The system that we have considered x1, x2, x3, xn, there are n number of variables, there are m number of equation, first equation, second equation, third equation, up to m number of equation. So this is one higher dimensional concept. We have not only 1, 2, 3 dimension, we have x1, x2, x3. How many variables we have? We have n number of variables. That means we are dealing with real numbers, but that real number is not in 1 dimension, not in 2 dimension, not in 3 dimension. That is in n dimension. Okay, so although we cannot draw, but we can analyze with mathematical concept. So At first, suppose we have a system like this. Ax equals b. So first of all, we have to write A and B matrix together. Here we have A and we have B. We have to write A and B matrix together. That is the first step of Gaussian elimination method, that is named after Carl Friedrich Gauss, German mathematician. So that is what I have written here. You have A matrix. A matrix is the coefficient matrix. B matrix is the right hand side constant matrix. Whenever we are writing this together and we are mentioning that there is one separation, this is actually denoting the separation bar. So whenever we are writing A matrix and B matrix together with some separation, then that matrix is known as augmented matrix. So the first step of Gaussian elimination method is to construct one augmented matrix. Then step 2. So in step 2, we have to perform row echelon technique. So what is row echelon technique? This is also known as elementary row operation. So row echelon. If we apply Gauss-Jordan technique, then that is known as row reduced echelon. But here we need just row echelon. It is also known as elementary row operation. So what is elementary row operation, or what is row echelon? It is actually easy. You have A matrix. Now from the A matrix, by matrix algebra or some operations, you have to convert A matrix, or you have to try to convert A matrix to this form: 1 0 0 1 0, then 1. If you have one system with 3 variables x, y, z, then your main target is to convert A matrix into this notation. Think about the diagonal. So here we have the diagonal elements. Suppose we have a matrix, you know that this is the diagonal. So the diagonal elements that you can see, these elements are somehow known as leading elements. Or leading entries. So your first target is to convert matrix A to this type of form. So in step 2, what is mentioned? You have to convert the augmented matrix to row echelon matrix. So what is row echelon? Row echelon will take this shape. So suppose you have some matrix, let's say there are some values here. You have a 3 by 3 matrix, let's say this is A matrix, and after row operation means you are trying to make 1 0 0 1 0 1 like that. I will describe how to make 1 0 0. So ultimately, suppose you have found one matrix that has this shape: 1 0 0 1 0 1, and there are some values here, let's say. So one example can be, let's say you have 1 1 1 0 0 0. Suppose you have 4 5, let's say -2. So suppose you have a matrix like this, let's say matrix B. So this type of matrix are known as upper triangular matrix. Have a look. You have values on the upper side, but the lower positions are with value 0. So these matrices are known as upper triangular matrix. Similarly, we can think about, suppose we have a matrix like this. Let's say we have 4 5, let's say 7, 2, -3, and let's say 6. But here you have this. So if we think about the diagonal, so above the diagonal we have some values, 2, -3, 6. But below the diagonal all entries are 0. So this is also known as upper triangular. So since we have a upper triangular, we may also have lower triangular. You can easily understand, suppose you have a matrix, let's say F matrix, and suppose you have 3 2, let's say 5. Here you have 3 4 and let's say 6, but in the upper position you have 0. So first of all, think about the diagonal. Below the diagonal you have some entries that are non-zero, but above the diagonal all values or entries are 0. So if we have this case, then that is known as lower triangular. So we have learned many definitions: rectangular matrix, square matrix, scalar matrix, diagonal matrix, identity matrix. We have learned determinant, minor, cofactor, non-singular matrix, singular matrix. Today here we have learned what is coefficient matrix, what is augmented matrix, and now we are learning upper triangular matrix and lower triangular matrix. So you have one upper triangular matrix here. That means here there are some values. At the same time, what I have written here, my target is to convert the diagonal entries from other values to 1. Have a look, I have written with 1. That is very easy. How we can write? That has some process I will describe. So from the coefficient matrix, if with some operations we can write the coefficient matrix with an upper triangular matrix like this, then this process is actually known as row echelon or elementary row operation. So this is step 2. So we will talk about step 2 again, but let's move to step 3 and step 4. So once we are done with step 2, then in step 3 we have to form again equations. Remember, from equations we have written this augmented matrix, and now after step 2, after having the upper triangular matrix here, this is upper triangular matrix. After having upper triangular matrix and the diagonal entries with 1, we will now start forming equations. That are the reduced equations that we will have. Now step 4 says that by back substitution technique, back substitution means we have, let's say, finally first equation, second equation, third equation. From third equation the result can be plugged in second equation. We are substituting. From third and second equation the results can be plugged in first equation. This is how we will get the solution X. Our main target is to find the solution set X, capital X. Inside capital X we have many variables, x1, x2, x3, let's say x, y, z, let's say x, y, z, w, anything. So this is about back substitution technique. So Gaussian elimination method is followed by another technique, that is back substitution technique. I know this is quite getting difficult for all of you to understand, but whenever we will solve some problem you will get the idea. Now let's get back to step 2. I have mentioned that there are actually 4 steps. Step 1, step 2, step 3, step 4. By these 4 steps you can easily solve any system. So step 2 is very important. How to convert this augmented matrix to row echelon matrix. So here you have 3 operations to consider. You are familiar with matrix algebra. You know matrix addition, subtraction, multiplication. So just like that we have some other 3 operations here to introduce, and that will be done here. So that 3 main operations are this. Suppose you have the augmented matrix from step 1. Now in step 2 you are trying to convert this matrix to upper triangular matrix, where the diagonal entries are 1 and the below parts are 0. So how to do this one? First of all, here you can see that there are 2 values, 1 and 0. For making 1 you have to use multiplication by a non-zero constant technique. Let me describe this one. Suppose you have a matrix, let's say 4, 3, 2, 2, 5, 7. Let's say we have -3, 0, 6. So how many rows and columns we have here? There are 3 rows, row 1, row 2, row 3, 3 columns, column 1, column 2, column 3. Now I want, let's say here 1. Instead of 4 I want 1. For some, let's say for some concept I need 1 here. For some application part 4 should be converted to 1. So how to do that? So that can be done by multiplication by a constant. So here instead of 4, if I need to write 1, you can easily understand that 4 can be multiplied by 1 by 4. At that time 4 and 4 can be cancelled, you will get 1. So that means in row 1, this is our R1, R2, R3. So I have mentioned that this row echelon technique, Gaussian elimination technique, applies row echelon. Row echelon means elementary row operation. So we are actually dealing with row operation, not column operation. Column 1, column 2, column 3, not like that. Okay, so we will deal with row operation. So we are targeting for 1 in this position of row 1. That means row 1 values are 4, 3, 2. So after some operation, if we multiply 1 by 4 with R1, that means 1 by 4 will be multiplied with all values of R1. So we are going to actually have a new row, let's say R1 prime, but other rows are same. R2 and R3 are same as before. 2, 5, 7, minus 3, 0, 6. We are not changing R2 and R3, but we are changing R1 prime. We are changing the first row by multiplying 1 by 4. So what is the answer you are getting? If we multiply 1 by 4 with R1, we are getting 4 and 4 cancelled, 1. 3 by 4, 2, 4, we are getting 1 by 2. So that means the new entries are, you can see, 1, 3 by 2, 1 by 2. So this is how we have found 1. And this technique is known as row echelon technique. So whenever you are making 1 by multiplication, that is one row echelon. Now you can also make 0, but for that we have another operation here, that is addition of 2 rows. But this type of operations are known as row echelon technique or elementary row operation. So this is how you can find 1 in any entry. Now suppose your target is to make 0. For that, multiplication is not allowed. Multiplication by a non-zero constant can be applied, but the main thing is you can only get 0. Any entry or any element in a matrix can be converted to 0 by addition of 2 rows. So let me describe this one also. Suppose now we have this new echelon matrix. So from this matrix we have found this new matrix. So every time we will do some operations and we will get new echelon matrix, and that new echelon matrix will be with R1, R2, R3. There is new R1, new R2, new R3. No need to write here R1 prime again. So consider that we have just R1, R2, R3. So now let's say we have here 2, but my target is to make 0 here. For making 0, we have to do additions of 2 rows. But remember that additions should be done with the leading row. So what is a leading row? I will describe here. So you can see that here we have 1, 3 by 2, 1 by 2, 2, 5, 7, minus 3, 0, 6. So we have this matrix. Now my focus is on here. So if we think about the diagonal, so this is the leading entry, this is the leading entry, this is the leading entry. So now we have to think column wise. Column wise, this is the leading element. Again think about this diagonal. This is leading element, this is leading element, this is leading element. The first element that you can see here, that is the leading element. Here the middle element that you can see, that is the leading element. Here the last element that you can see, that is the leading element. That means think about the diagonal wise in general sense. Whatever entries that you can see, that is the leading elements. Now if we think column wise, column 1, column 2, column 3. So column wise, this row 1 has the leading element. This is the leading element. For column 2, this will be the leading element, not 3 by 2, not 0. For column 3, this will be the leading element. 6, not 1 by 2, not 7, 6. So that means for column 1, the leading element is found in row 1, not in row 2, not in row 3. For column 2, leading element is found in row 2, not in row 1 and row 3. So I hope you are getting the idea. For column 3, this is the leading element that is found in row 3. So this is how you will get the idea of leading element or leading entry. And leading entry is related to the row and column. Okay, however, so we have this matrix, and this time our focus is to make this entry 0. So for 0 we have to use addition. So we have total 3 rows, R1, R2, R3. But R1 and R3 are same as before. But we have to change R2. That means we will get a new row, R2 prime. But here we need 0. That's why we have to do addition. So how to do this? Here R2 prime can be found. Let me do some side note here. Let's say this is the extra work that you have to do. So R2 prime can be with 0 entry if we do addition of R2 with R1, because in R1 we have the leading entry. So now this 2 can be made 0 if with R1 we multiply -2 R1, and if we now add with R2, then this can be made 0, because here you will get -2 times 1 -2 plus 2, you will get 0. So this is how we can make 0 here. So that means to make 0 we need -2 R1 plus R2. So let's do this calculation. So R1 values are 1, 3 by 2 and 1 by 2. If we multiply -2 with all the R1 values, that means it will be -2, it will be -2, it will be -2. So the result that we are getting minus 2, then here 2 and 2 cancelled, we are getting minus 3, 2 cancelled, we will get minus 1. So this is minus 2r1. Now r2, I am just doing the rough calculation. In r2 we have the entries 2, 5, 7. Now what do you have to do? The formula says that minus 2r1 and r2 should be added. So let's add. You will get r2 prime. So minus 2 and 2, 0. Minus 3 plus 5, 2. Minus 1 plus 7, that is 6. So that means new r2 will be 0 to 6. So 0 to 6. Have a look, we have found 0. So this time 0 has been found. So from here to here, this is one matrix. From here we have found a new matrix. Whenever we are dealing with 1 and 0, making 1 and 0 will give you new matrices. That matrices are known as echelon matrices or echelon matrix. So this is what we will do in step 2. And lastly, we have another operation that is also feasible, that is also convenient to make directly 1, directly 0. That is interchange of two rows. Suppose you have a matrix, let's say 4, 3, 2, 1, 4, let's say 5, 2, minus 3, 8. Suppose you need 1 in the first row. So for that, what do you have to do? You have to multiply 1 by 4 with row 1. But if we want, we have 3 rows here, R1, R2, R3. If we want to make 1 here, we can interchange R1 and R2. This is the interchange symbol. So R1 and R2 are interchanged. That is, R2 values will be R1 and R1 entries will be in the position of R2. So see, we have found 1. So 2 minus 3, 8, that is R3. R3 is same as before, no problem. But we have interchanged R1 and R2 just to get 1 here. So remember, for making 1, always you have to do multiplication with a non-zero constant. For making 0, we have to do addition of 2 rows. But besides these 2 operations, we have also another thing, that is interchange of 2 rows. If we can see that interchange can be done, you can easily do that, because you can see 1 here that can be interchanged and written here. So this is how we can do the interchange. So while doing interchange, there will be no change in sign. Have a look. In R2 we have plus 1, plus 4, plus 5. Same values are written here. In R1 we have 4, 3, 2, plus 4, plus 3, plus 2. Same values have been written here. So whatever we are doing, that are known as row echelon or elementary row operation, that is based on these 3 techniques, and that we have to do in step 2. So have a look again on step 2. Your target should be making 1, 1, 1. The diagonal entries should be made 1. So if you cannot do that, no problem. That will give you actually one new conclusion. We are trying to make 1, 0, 0, 1, 0, 1. We are trying to form upper triangular matrix here. But going with this process, if ultimately we are stuck, then we may have many solutions, we may have no solution. But if we are easily getting 1 1 1 in the diagonal portion, then that will give us one solution or unique solution. You know that a system may be consistent, may be inconsistent. If we have a consistent system, that will be with one solution, maybe with many solutions. So for one solution we will get a complete upper triangular matrix. For many solutions we may not get that. For no solution, you will see that there will be some equations that is violating the law. Suppose you are getting ultimately 0 equals 5. So that is actually violating the law. 0 and 5 are not same. So this is the way how we will do. So today just we have tried to understand the steps of Gaussian elimination method. There are 4 steps. Step 1, step 2, step 3, step 4. Step 1 is to make augmented matrix. Step 2 is to use row echelon technique. Step 3 is to form equations. Step 4 is to use back substitution technique. Now suppose you have 2 equations, 2 variables. Let's say 2x plus 3y equals 5, x plus 2y equals, let's say, 6. So if we have to solve these systems, then we will apply Gaussian elimination method. So first step is to write in A separation D form. You can see here A will be 2, 3, 1, 2. These coefficients. B will be 5 and 6. X is the solution set. How many variables you have? X and Y. So X and Y is making X set. So step 1 is to write by this. A matrix. A matrix is 2, 3, 1, 2. There is a separation that we are giving, and here we have 5, 6. Now in step 2, what we have to do? We have to make, anyhow our target is to make 1, 1, 0, and there will be some value, and automatically this right side will be changed. Here you can see 5 and 6, but these things will be changed. So after then, let's say step 3 says that form again equations. You know that this part this column will be for x. Have a look. In x column you have 2 and 1. So in x column we have 2 and 1. In y column we have 3 and 2. So this is y column. In this b column we have 5 and 6. And this separation is actually denoting the equal sign that you can see. So whatever we have equation format that we have that have been written in matrix form. So if we think 2, 3, 5, that means we have 2x plus 3y equals 5. If we think 1, 2, 6, that means we have 1x plus 2y equals 6. That is how we are thinking. So this first column is for x, the second column is for y, and the third column is for b. Now recall how many steps you have. You have step 1, step 2, step 3. In step 3 you have to again form equations. So from here, suppose you have 1x plus something equals something. This is how you are maintaining equations. Here you have 0x plus 1y equals something. So no need to write 0. So ultimately you have these 2 equations. Let's say this is equation 1, equation 2. Now step 3 is done. Recall what is step 4. Have a look here. Step 4 says that use back substitution technique. So that means If we use back substitution technique, that means from second equation we have y value already. Our target is to get the solution x and y. What is x and what is y? You have the value of y already. Y can be plugged in equation 1. You will get x. This is how you will get x value, you will get y value. That means the solution is found. So you may have one solution, you may have many solutions, you may have no solution. Ultimately, suppose you have two variable problem. You have x and y only. Let's say x1 and x2 only. Then you should stop here. 1, then 0, then 1, and there will be some value. If you have three variable problem, there is a system with x, y, z. Let's say x1, x2, x3. Then in step 2 is very vital. In step 2, you have to target for making 1, 0, 0, then 1, then 0, then 1. And here there are some non-zero values. Suppose you have 4 variable, although that is not included here in this content, but you can think about that. Suppose you have 4 variables x1, x2, x3, x4. At that time, you should think for 1, 1, 1, 1, 0, 0, 0, 0, 0, 0. Here you have some values, let's say. So think about the pattern. If we have 2 variable, 3 variable or 4 variable, our target is to make the diagonal entries 1. If we think about row wise, we are targeting for making this leading entries 1. These are known as pivot or leading 1. Pivot element or leading 1. Okay, so this is how we will think about in step 2. Lastly, if we get, let's say we get here in this case, or let's say in this case, or let's say in this case. Let's think about a 3 variable case. So we have, let's say 1, 1, star, 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 0, 0, 0. Here hysteric means we have some non-zero values. So our target is to make 1, 1, 1 here. But somehow, suppose we have found here 0. We know that there are 3 operations: multiplying by 1, or addition of 2 rows, or interchange. So whatever method we are applying, we are actually getting 0, not 1. So if this is the case, let's say, now suppose, have a look, this separation is actually denoting the equal sign. So ultimately after step 2 we will form equations. So if this is also 0, the right side value is also 0, so think about the last equation, 0 plus 0 plus 0 equals, if the right side is 0, then ultimately you are getting 0 equals 0. So that means 0 equals 0 is a valid equation, but we don't need to write this. So we are actually getting 2 equations. How many equations we have here? Let's say 2 equations ultimately, although we have started with 3 variables and 3 equations, but after row echelon technique we have found only 2 equations. So that means one equation is missing. So total number of variable we have 3, and lastly we have found one equation missing. That means we have only 2 equations. So if we try to subtract these numbers, that is 3 minus 2, variable minus equation, then we will get the number of free variable that we have. So there is another definition here. What is free variable? So free variable equals variable, number of variable minus number of equation. The column or row that doesn't have any leading one. Have a look. This is the column for X, this is the column for Y, this is the column for Z. So this X column has leading 1, this Y column has leading 1, this Z column doesn't have leading 1. So we have 3 variables actually, X, Y, Z. But X has leading 1, Y has leading 1, but Z doesn't have leading 1. So that means this Z is the free variable. Free variable allows us to take any parameter, any value. Let's say Z equals A. Automatically, if you input Z in Y equation, you will get some function of A. You will get also X as function of A. So that means you are getting many solution, because A is any real number. You can also think about T. T is any parameter instead of A, but the parameter is actually real number. So this is the idea that if 0 equals 0 is coming, then you will get many solution. Suppose for some system we are trying to make 1 1, then here we have 0 0 0, here we have some star star, but instead of 1 here we have 0. Now think about the last equation. Here we have 0 plus 0 plus 0. Now if this star is a non-zero value, let's say 5, so ultimately you have 0 equals 5. That means 0 equals 5 is not valid. So the system that we have is with no solution. So these are the 3 techniques that you will have: no solution, many solution, and one solution. For one solution you will get a complete triangle, you will get complete upper triangle, and all the diagonals will be with 1 1 1. So this is what we have, the theoretical approach. Now you can have a look on this note. The problems have been solved, and try to understand this. We will discuss the problem solving part in our next session. Today whatever we have discussed, that is the theoretical approach. So that's all for today. Thank you.